So on the final exam, there'll be a section on work and energy. And basically, the idea of energy, it's really the capacity to make change. It's a capacity to make changes in your environment. And energy comes in many different forms. There's lots of ways of seeing energy in the universe. The way we introduced energy, though, was to imagine a very simple situation where we had a cart with a net force on it. And we applied that net force through some displacement, delta x. And now think about this. This is an action. We're applying a force to something, and it's going faster and faster and faster. So somebody is using energy because we're affecting a change. Now what we want is some way of exactly defining that energy. And so what we did was we said, well, here's the change we're making. Force times, let's take a look at force times a displacement. Well, so this force was, if you look at this is the net force on the object. And we know that the net force is equal to mass times acceleration. The net force is equal to mass times, now what we're going to do is we're going to express this in terms of velocity. So this thing, if you apply a net force through a displacement, this object is going to be moving. And so what we know is, we can look at the second kinematic equation. The velocity squared is equal to the initial velocity squared plus twice the acceleration times delta x. So what we did is we solved this for the acceleration, and the acceleration is v squared minus v naught squared over 2 delta x. So this is the net force, mass times acceleration. And so what we did is we substituted this for the force in here. So this is the mass times v squared minus v naught squared divided by 2 delta x. And then we said we're going to multiply this by delta x. So this we've just carried from over here. And so this was force times delta x is equal to, well, let's clean this up. Delta x cancels. I've got to divide by 2, so that's going to be 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. So I just re-derived it, and I did it fairly quickly. But this product right here we call work. 1/2 mv squared we call kinetic energy. And since we have a final velocity and initial velocity, this is a change in kinetic energy, where kinetic energy is 1/2 the mass times the velocity squared. This is the definition of kinetic energy. So work equals, so we use the letter W to represent work, equals the change in kinetic energy of an object. This is Mr. Lake.
Hello.
Yeah, but I didn't. She hasn't called. And if she doesn't want it, it'll go to anybody. Yeah. Thank you. This is called the work energy theorem. And it's a fundamental law of physics. Basically, this force right here is the net force. Net force. And if the net force does work, you're going to change the kinetic energy of the object. And kinetic energy is the first kind of energy we talked about. It's the energy of a moving object. If an object is moving and it has mass, it can affect change, okay? So just, imagine something with mass moving really fast and hitting you, right? Like somebody throws a baseball at you, it's going to do some work, right? It's going to affect the change, and and we saw different kinds of energy, like let's talk about gravitational potential energy. If I've got the ground and I've got like a bowling ball or something like this. Okay, it's got a certain mass and it has a height above the ground. There's our height above the ground. Now, we say gravitational potential energy is the work gravity can do. Okay, so gravity can do work on this ball. How much work? Well, for it to reach the ground. Well, we have the force of gravity here, right? And the force of gravity is the mass of the ball times g, the acceleration of gravity. And we said that work is equal to a force times the distance. But here, the force is mg. Your distance, delta x, is your height. And so for potential energy, we use the letter U to represent potential energy. So the potential energy due to gravity is equal to mgh. Now, h is the height above our reference, usually the ground. But if let's say you dig a hole and you put the bowling ball down here at the bottom of this well. Here you can say you've got a negative height. Okay? That is, just to get it to zero, you have to put work into it. You have to lift it out of the well. So gravitational potential energy can be negative. If your height is below where you measure height from. You measure height from here, well, this height is above the ground, so you have positive gravitational potential energy. But here, the bowling ball is below ground, so you're going to have negative gravitational potential energy. So unlike kinetic energy, which is always positive, gravitational potential energy can be negative. Now, if I let this ball fall down, we're losing gravitational potential energy. Gravity is doing work. When gravity does positive work, we lose gravitational potential energy, but it's the only force acting. So it's the work done by the net force, and therefore we're gaining kinetic energy. And so we have this concept, and again, we're just reviewing. You should have this concept already in mind. We have this concept of mechanical energy. Now, mechanical energy was defined to be, and we'll use a capital E. Mechanical energy is defined to be how much kinetic energy the object has plus how much potential energy it has. And we're just going to stick, for the final, we're just going to stick with gravitational. There are other kinds of potential energy. There's elastic potential energy, that's energy stored in a spring, and there's chemical potential energy, and so on, although that's not mechanical. But so we'll just leave it like this. Now, if the only force doing work is gravity, and gravity is the net force, then that net force will change the kinetic energy. But if it's got kinetic energy, and gravity's doing negative work, it's just going to turn that into potential energy. Christian, this is for you. Okay. So, if the only force doing work is gravity, then the amount of mechanical energy then is constant. We're not going to change the amount of mechanical energy in the system. Like if you take a ball and you throw it up, okay, as the ball goes up, it goes slower and slower, so it has less kinetic energy. But it's got more and more height, so it has more gravitational potential energy. The potential energy it gains is exactly equal to the kinetic energy it lost. And this is, of course, assuming that there's no wind resistance or anything like that. But that's what we mean by the only force doing work is gravity. So you'll have problems where the mechanical energy is conserved. And so the way to set up those problems would be to do this. If the only force doing work on gravity, then E is constant, then you can say the initial energy is equal to the final energy. And so you would set this up and solve the problem. Also, one thing I want you to know about work. Work is the transfer of energy by a force. We're transferring energy by use of the force. Like when the ball falls, gravity is doing work by the use of the force of gravity. So it's doing work, it's transferring energy. When you push on, when we go back and look at this picture, this is what we mean by work. Somebody had to have energy, and by applying a force through a displacement, they transferred that energy from their bodies into the object. So work is a transfer of energy through the use of a force. Now, but one thing I want you to remember is that work is equal to the force times the displacement. We'll call it delta x. It can be delta r, delta y, whatever you got, times the cosine of the angle between the force and the displacement. So if I give you a problem like this, which is very likely on the final, I might give you a problem where there's a force, there's a displacement, and there's an angle theta. And you would have to say, okay, it's only the part of the force that's in the same direction as the displacement that does any work. If I take this force, F, and I break it up into its components, well, it's this component that's doing work because it's in the same direction as the displacement. Well, this is F cosine theta. So that's where we get F cosine theta times delta x is the work done. Notice this right here, this component of the force, it's not doing any work because it's not in the direction of the displacement. It's not transferring energy from the outside agent into the crate. Only this component is. Any questions? Okay. Getting back to this, you'll have the kind of problems I have on the final. on work and energy. Definition of work. I have a force, I have an angle, I have a displacement. You have to figure out the work. It's very basic. Kinetic energy calculation. And one thing, I have a roller coaster problem on it. Do you remember how to do roller coaster problems?
Oh, yeah.
Okay, so if I've got a car that's going certain speed, here's a roller coaster car, like California Screamin', and then it's going to go up to the top of a hill, and it's coasting. So the energy it has here has got to be equal to the energy it has up here. So this is going to be 1/2 mv squared plus mgh. But of course, what is h down here? If I measure h, we'll say, okay, this is 0, so this term doesn't apply. But maybe up here, it's still moving, right? So it's got a certain height. And so this is going to be equal to 1/2 mv squared plus mgh. Now we'll call this the initial, and we'll call this the final to distinguish the velocities. Okay, but can you solve for the height? Yes, if I give you this final velocity, you can figure out how high it went. But what if I give you the height? Can you solve for the final velocity? Yes, you can. It's just algebra. So you're going to have a problem where it's going to be this simple. You're going to look at the energy of the roller coaster car before and after, and then you'll have to figure out how high it is or what its final velocity is. Can you do that?
Yes, sir.
Okay. And that is it for work and energy on the final exam. Ryan? Why? Oh, Ryan wants to be part of history. Okay. Good job, Ryan. Volleyball playing Ryan. You got to beat Sanger.
And he looks cute in that t-shirt he's wearing today.
Oh, the world will never know.